So welcome back. We're going to continue working with the derivative today, with the definition of the derivative. So we want to find the points on y equals 1 over x such that the gradient of these points is negative 1/9. So if you remember, 1 over x looks something like that. We want to know where the tangent has a slope of negative 1/9. So something like that maybe, and something like that. Can you envision that there will be two solutions to this? I hope so. But let's go ahead and find them. So we need the gradient at some point on this curve, so we're going to find the derivative. There's that derivative formula that we saw in the previous video. So let's use it. 1 over x plus h minus 1 over x over h. Okay, now this gets a little bit involved because we have to combine some fractions together. We need a common denominator. Remember what we do to the bottom, we must do onto the top. So the numerator becomes x minus x plus h over, and this is all divided by h. And of course, I forgot to write limit, h goes to 0. So now the limit, h goes to 0 of, well, in the numerator we just have negative h over x squared minus xh divided by h. So remember, dividing by h is really the same thing as multiplying by 1 over h. We have the limit h goes to 0 of negative 1 over x squared minus xh, x squared plus xh. So now we take the limit. We don't have over h anymore. We can now do our direct substitution. So we don't need the limit anymore. This is equal to negative 1 over x squared. This term will go to 0. So our dy dx, our derivative of 1 over x, is negative 1 over x squared. And remember, derivative finds us the slope of the line tangent to the curve. So we want to know, where does this equal 1/9, negative 1/9. So x squared needs to equal 9. X is positive or negative 3. So the points, the actual ordered pairs where the tangent line will have a slope, a gradient equal to negative 1/9, are 3, 1/3 and negative 3, negative 1/3. Next example. If f of x is the square root of x, find the derivative. Hence, that means use what we just did. Find the equation of the tangent line at x equals 4. Also find the equation of the line normal to the curve at x equals 4. Well, first, x equals 4 means the ordered pair 4, 2 is on f of x. We'll need to know that when we write the equation. But first we need the derivative. Limit h approaches 0 of f of x plus h minus f of x all over h. So, what do we do here? Well, we need sort of the square roots to go away in the numerator, And you may remember that when we want the square roots to go away in the denominator, we rationalize, we multiply by the conjugate of what's down there. We're going to use that same skill, but we want the radicals to go away in the numerator. So, we're going to multiply by square root x plus h plus square root x. And this will leave us in the numerator with x plus h minus x. Then we also have to multiply the denominator. And now notice, numerator, the x's go away, and I'm left with just plain old ordinary h, and I'm left with h and look what happens. The h's can go away, and that pesky h that was in the denominator that was preventing me from doing direct substitution is now gone. Yay, that's wicked, great, cool, awesomeness. So now we can do our direct substitution. We put the 0 in for h. That first term in the denominator approaches square root of x plus square root of x. Our derivative is 1 over 2 square root x. So slope of tangent at x equals 4 will be m equals 1 over 2 times square root of 4, also known as 1/4. Okay, let's jump to the calculator for a second. Here's our graph, square root of x. Remember, if we want to check our derivative calculation, we can analyze graph dy dx, and I'm interested in x equals 4, so I type 4, push enter, and there we go. The slope is 1/4. That's great. But now I need the equation of this. Remember how we find equations of lines, guys. Y minus y1 equals m times x minus x1. Our slope we just found is 1/4, and the point that we're working with is 4, 2. That's the point where our tangent line hits the graph. So y minus 2 equals 1/4 times x minus 4, y equals 1/4 x minus 1 plus 2, add 2 to both sides, so y equals 1/4 x plus 1. There is the equation of my tangent line. Now this problem also asks for the line that's normal to the curve. What does that mean? So there's our square root graph. That's roughly the equation we just found. The line that's normal to that would be perpendicular to the tangent. It's perpendicular to that curve at that instance. So, do we remember what the slope of perpendicular lines are? Well, if m is 1/4, the slope of the perpendicular would be the opposite reciprocal. And now we're still using the point 4, 2. So y minus 2 equals negative 4, x minus 4, our point slope form. Y equals negative 4x plus 16 plus 2. Y equals negative 4x plus 18. This is our normal line at x equals 4. This is our tangent line at x equals 4. Okay, last thing to talk about today is whether or not something is going to be differentiable. So we have the function f of x equals square root x. Is that always going to be differentiable? Well, I'm going to look at a graph. So I'm going to go with this square root graph, and I'm going to zoom in. I'm just going to pick right here. Zoom in, zoom in, zoom in. If you're zooming and the curve appears to become linear as you zoom in really close, it's safe to say that that graph is differentiable at that point. However, here's our square root graph. if I zoom in here at a specific spot, if I zoom in at this vertex of the absolute value graph, is that approaching a straight line? And I hope you're saying, no way, that is not approaching a straight line. That means that this absolute value graph is not differentiable at x equals 0. The square root graph also is not differentiable at x equals 0. The graph just stops there. It doesn't approach a straight line. So what this tells us is if, I'm going to give you two statements here. If a function is differentiable at c, it is continuous there. So if you're able to find the derivative at a particular point, you know that it's continuous. However, if a function is continuous at c, it is not necessarily differentiable, as we saw with the absolute value graph and the square root graph. Just because that graph is continuous, just because our square root graph or our absolute value graph is continuous at x equals 0, there's no break, but that doesn't guarantee that we can differentiate there. And we can't differentiate there because it is a sharp point as opposed to a smooth curve. And we can zoom in on a graph to make that determination. And that, ladies and gentlemen, is where I shall leave you today.